Welcome back to the deep dive. Okay, today we're strapping on our virtual hard hats. We're plunging into something that dictates, well, basically how everything around you gets built. But most people, they never give it a second thought. Building codes.
Right. And they probably sound like, just stacks of incredibly dull technical manuals. But our mission today, really, is to show you that the building code isn't some arbitrary checklist. It's actually a highly structured system.
Like a philosophy.
Sort of, yeah.
Yeah.
It's like the philosophical contract behind safety, health, structural integrity, and coordination in everything we build.
So we're going past the blueprints, trying to figure out the logic, the why behind all the rules, because
Huh.
every little detail seems like how wide a hallway is to, I don't know, the thickness of a wall.
Yeah.
It all ties back somewhere.
It does. It ties back to that foundational intent, ensuring safety, health, accessibility, yes, but also energy performance, environmental protection. It's broad.
Okay. And you're saying to really get the logic, we need to start with the language itself. Definitions.
Absolutely critical. Definitions carry huge legal and technical weight. They can instantly decide the whole scope, the cost, everything for a project.
All right, unpack that for us. Give us a concrete example. How can one defined word, just one word, potentially change a project's budget by millions?
Okay, look at the difference between, say, renovation and reconstruction. These sound similar, right?
Yeah, pretty close.
But in code terms, a minor renovation, maybe you're just renewing finishes, putting in new carpets, that kind of thing.
Surface level stuff.
Exactly. You might avoid triggering major, expensive life safety upgrades required by the current code.
Okay, that sounds like, sensible maintenance, cost effective. But where's the line? What pushes you into needing full compliance?
That happens when you cross into reconstruction. Now, that definition implies substantial rebuilding. It means you're significantly affecting structural elements or core life safety systems.
So messing with the bones of the building.
Precisely. And suddenly, you might be required to bring that whole area, maybe even the whole building, up to all modern safety standards. That could mean seismic upgrades, full sprinkler systems, things that weren't required when it was first built.
Wow. So the definition is basically the switch that flips the compliance level and the budget.
You got it. That's the power of precise language here.
Okay, that really sets the stage for how this whole system works. If the definition tells us what we're doing, then the scope tells us where these rules actually apply. So what's the code's jurisdiction?
Well, it covers every new building, obviously. That's the baseline. But crucially, it also applies to additions, modifications, and, this is a big one, any change in the use or occupancy of an existing building, especially if that change affects safety or increases risk.
Give me an example of change of use.
Okay, imagine someone takes an old, say, two-story school building and wants to convert it into luxury apartments.
Right, happens all the time.
Well, that completely changes the occupant load, the exit paths needed, the fire risk profile, everything. The code snaps into effect instantly for that conversion.
Interesting. What about things it doesn't cover? Are there exclusions?
Oh, definitely. Highly specialized infrastructure usually falls outside the main building code. Think major bridges, tunnels, power plants.
Things that aren't really buildings in the way we live or work in them.
Exactly. They're governed by separate, very focused engineering standards because their primary risks are different. A bridge needs to handle massive loads, wind, maybe earthquakes. Different priorities than, say, an office building's fire safety.
Which brings us to a coordination challenge, right? The code can't possibly contain every single piece of technical knowledge for every material or system. How does it connect to all those external standards? The specifics of how concrete should be mixed or steel beams bolted?
It does that by incorporating them by reference. The code essentially says, okay, designer, this is the performance you need to achieve. For example, a column must withstand this specific load. Then it points to widely accepted, peer-reviewed industry standards, like those from ACI for concrete or AISC for steel structures, to tell the engineer how to actually calculate and achieve that required performance in detail. It relies on that external expertise.
But surely in the real world, with all these different documents, the main code, the fire code, the structural standards conflicts must pop up sometimes. Maybe one says one thing, another implies something slightly different.
They do. It happens. And the system has a built-in way to handle it.
Which is?
The key principle is usually about hierarchy and stringency. If there's a conflict between one of those referenced standards and the main building code itself,
Yeah.
The requirement that is generally more specific, or the one that is more stringent, meaning safer or tougher, usually takes precedence.
Ah, so err on the side of caution, basically.
Essentially, yes. It's a
Okay.
mechanism designed to ensure that if there's any doubt, maximum safety is the default outcome.
That sounds potentially quite rigid, though. We see architects designing really innovative, unusual buildings all the time. Does the code just crush creativity, force everyone into boxes?
It shouldn't, and that's why there's a crucial provision for something called alternative solutions. The system explicitly allows for innovative materials or construction
As
methods,
long
as
as?
long as they can be properly justified, documented, and demonstrated, often through engineering analysis or testing, to achieve performance that is equivalent to or even better than what the standard prescriptive rules require.
So it encourages innovation, but within that safety framework.
Exactly. Keeps the door open for creativity without compromising that fundamental safety contract we talked about.
Okay, so that's the kind of technical roadmap for the building itself. But let's zoom in a bit. Let's move from the framework to the actual people inside the building.
Mhm.
How does the code stop a designer from creating a space that's technically safe, maybe, but just awful to live or work in?
Well, that's the whole point of the sections on spatial requirements. These aren't just about safety. They translate health research and human ergonomics directly into minimum dimensions.
Ergonomics, like how we move and interact with space.
Precisely. They aim to prevent design compromises that might sacrifice basic livability, things based on movement, air quality, natural light.
Give us some concrete examples. What kind of human dimensions are we talking about?
Well, think about a kitchen. It's a critical workspace, right? Often busy. The code might require a minimum total square footage, sure. But maybe more importantly, it often mandates minimum maneuvering space.
Like room to move around.
Yeah, like a clear 1.2 meters maybe between counters or appliances. That number isn't just pulled out of thin air. It ensures you can safely open an oven door without hitting someone, or that two people can actually pass each other without bumping. It prevents accidents, burns.
Makes sense. And what about ceiling heights? Is that just about feeling cramped, or is there more to it?
It's more than just avoiding feeling like you're in a cave, although that's part of it. Adequate height is really crucial for proper air circulation, helps distribute light effectively. And the codes usually define the clear height that's the usable space after all the stuff is installed in the ceiling, like ductwork, pipes, sprinklers.
Ah, so the actual headroom you end up with.
Right. Without that minimum clear height, spaces can feel stuffy, poorly lit, and just generally less healthy.
Okay. This focus on how people move naturally leads us to accessibility, or universal design. We often think of ramps and accessible restrooms,
Which are vital, of course.
but it sounds like it's a broader concept than just
Oh,
the...
much broader. It's really a philosophy of barrier-free design that aims to benefit everyone. Yes, it helps people with permanent disabilities, absolutely.
Mm,
But think about someone with a temporary injury, like on crutches, or an elderly person, or even a parent pushing a stroller, or delivery staff with a cart. Good accessible design helps them all.
So things like ramps benefit more people than just wheelchair users.
Exactly. The code mandates things like the accessible route that needs to be a continuous obstacle-free path through the building, and specifies standards for door widths, counter heights, ramp slopes, yes, but also things like lever door handles instead of knobs.
And this accessibility focus, it can't just disappear in an emergency, right?
Never.
Mhm.
Safety has to be universal. That's critical. So, modern fire alarms, for example, require both sound and visual signals, bright flashing lights for people who are deaf or hard of hearing.
I see.
And for multi-story buildings, if someone can't use the stairs during an evacuation, maybe they use a wheelchair or have mobility issues, the code mandates specially protected refuge areas. These are fire-rated safe spots, usually near stairwells, where they can wait safely for assistance from emergency responders.
So everyone has a plan, an equal chance of safety.
That's the goal.
Okay, let's move deeper into the structure itself. Part 3, integrated systems. And let's start with maybe the most critical one, fire safety. You mentioned compartmentation earlier. What exactly is that, and why is it so vital?
Compartmentation is, quite simply, the core life-preserving strategy in fire safety design. It's about dividing a building into sealed zones, or compartments. We know that smoke often kills more people, and faster, than the actual flames in a fire.
Right.
So the code requires walls, floors, and ceilings separating different areas or different occupancies to have a specific fire resistance rating. That means they're built and tested to resist fire penetration for a set amount of time, often 1 or 2 hours, sometimes more, depending on the building type and risk.
And the goal is to contain the fire.
To contain the fire, yes, but maybe even more importantly, to contain the heat and the lethal smoke, slowing its spread through the building. It buys precious time for people to evacuate.
And I imagine protecting the vertical connections, the stairwells. Elevator shafts must be absolutely paramount because smoke and heat rise so quickly.
They are the escape lifelines. They have to be protected. Staircases, elevator shafts, any vertical opening that cuts through floors must typically be enclosed in construction with a high fire rating. This is designed to keep those roads clear and as smoke-free as possible so people can actually get out.
That's where, as you said, the technical details really mean life or death.
Absolutely.
Okay, shifting from fire to the actual bones, the literal skeleton of the building. Structural integrity. Structures feel permanent, but they're designed with a lifespan in mind.
They are. Durability is a key consideration. Codes usually specify a minimum design life. For typical residential or commercial buildings, that might be 50 years.
And for more critical buildings,
For essential facilities, hospitals, emergency response centers, maybe major public venues, it could be much longer, potentially 100 years or more. They need to be functional after a major event. And achieving that relies on engineers ensuring there's a continuous load path.
load bank.
You mean the weight of the building itself, plus occupants, snow, wind loads, everything. It all needs to be reliably and continuously transferred from the roof, down through the beams and columns, all the way to the foundations and into the ground. Every connection matters.
You also mentioned something called robustness against disproportionate collapse. That sounds serious and probably expensive to design for. Is the code saying redundancy is basically non-negotiable?
In many larger or more complex structures, yes, it effectively is non-negotiable, and it's a requirement that came directly from learning harsh lessons from real-world tragedies.
Like what?
Well, the classic example is the Ronan Point Tower collapse in London back in the 1960s. A relatively small gas explosion took out one corner's load-bearing panels, and it caused a progressive collapse of a whole section of the building. And you could argue lessons from events like the Oklahoma City bombing also reinforce this need. The principle is that the failure of a single localized structural element, one column, one section of wall, due to an accident or unforeseen event, should not trigger a catastrophic cascading failure of the entire structure or a disproportionately large part of it.
So the design needs built-in backup paths for the load.
Essentially, yes. It requires designing for alternate load paths or sufficient internal redundancy, so the structure can bridge over localized damage without that kind of pancaking or peeling effect. It adds complexity and cost, yes, but it's a fundamental safety requirement now for many building types.
That's a powerful example of how codes evolve from failure. Okay, let's look at moving within the structure. Vertical transportation elevators, especially in taller buildings. What's the key design goal there?
Efficiency, really. Efficiency under pressure. The core metric engineers use is handling capacity.
Handling capacity.
It's defined as the maximum number of people an elevator group, a bank of elevators, can typically move in a 5-minute period, usually during the busiest morning rush hour.
The morning peak?
Exactly. If the system can't meet the calculated handling capacity for that building's population, you end up with massive queues in the lobby, frustrated occupants, wasted time, and potentially even safety issues if people can't evacuate efficiently in other scenarios.
And are there requirements for the elevators themselves? Like for energy use, they must use a lot of power.
Oh, absolutely. Energy efficiency is a big focus now. The code often mandates energy-saving features. A common one is variable frequency drives, or VFDs.
What do they do?
They're essentially smart motor controllers. They regulate the elevator motor speed and torque much more precisely than older systems, matching the power needed to the actual load and speed, which saves significant energy, especially during off-peak times. Codes also often require low-power standby modes for when the cars aren't in active use.
And we also see fancier systems now in new buildings.
Yeah, things like destination control systems. That's where you select your floor before you even get into the elevator. The system then groups passengers going to similar floors into the same car, which minimizes the number of stops and makes the whole trip faster and more efficient, especially in very tall, busy buildings.
Interesting. Okay, the final piece of these integrated systems seems to be the indoor microclimate. So the code is actually setting standards for comfort and health, not just safety and structure.
Correct. It recognizes that the indoor environment directly impacts occupant health, well-being, and productivity. So it often mandates maintaining thermal comfort within a fairly narrow range.
Like a specific temperature.
Yes, often specifying target ranges, maybe somewhere between 22.5 and 25.5 degrees Celsius, for example. And managing humidity is also key, typically requiring systems to keep it within a healthy range, say 30% to 60%, to prevent issues like mold growth or respiratory irritation.
What about the air itself, the air we breathe inside?
Critically important. The code mandates a guaranteed supply of fresh outdoor air ventilation. It often does this by referencing other rigorous standards, like those from AHHRAE, the American Society of Heating, Refrigerating, and Air Conditioning Engineers, which set minimum ventilation rates based on the space type and occupant density. Plus, there are often requirements for testing the air quality before the building is occupied.
Testing for what?
Things like volatile organic compounds, VOCs, which can off-gas from new carpets, paints, furniture, and also checking for other airborne particulates. The goal is to ensure good indoor air quality from day one and prevent potential sick building syndrome issues.
And one more sense sound. Does the code deal with noise?
It does, increasingly so.
Yeah.
Noise control is recognized as essential for comfort and even health, especially in places like apartments, hospitals, or schools. So codes might require specific sound transmission class, STC ratings for walls and floors between units, or set maximum background noise levels from building systems like ventilation, demanding quieter designs and sound-rated materials.
Okay, this is fascinating. For our final segment, let's try to bring all these principles down to earth. Let's apply them to something tangible, like a typical residential project, maybe a villa or a townhouse. Part 4, real-world application.
Right, this is where many of these concepts really hit home for people. You see the interplay of fire safety, privacy, planning rules, all in your own backyard, potentially.
Let's start with the space around the house. Setbacks. The rules about how close you can build to your property line.
Crucial. For typical residential plots, codes almost always govern setbacks. You often see something like a minimum 3-meter setback required from side and rear property lines for the main house.
Why 3 meters specifically? Is that arbitrary?
Not really. It serves a few purposes. One is obviously providing a degree of separation for privacy from your neighbors, but maybe more critically, it provides space for fire safety access. It gives firefighters room to get around the building with hoses and ladders, and it also helps reduce the risk of fire spreading from one house to the next by providing a buffer zone against radiant heat.
Makes sense. What about other structures on the plot? Like a detached garage, or maybe an external kitchen, or a pool house, annexes.
Annexes are usually strictly regulated too, mainly to stop them from overwhelming the plot or creating fire hazards. While sometimes they can be built closer to the property boundary than the main house, maybe even right on it,
Yeah.
they almost always have to maintain a minimum separation distance from the main house itself, often something like 1.5 meters. Again, that's primarily for fire safety, to prevent fire jumping easily between the main dwelling and the annex. There are usually limits on their size, too. Maybe they can't exceed 60% of the main villa's floor area, for example.
Okay. And since we're talking about the outside space, let's touch on pool safety. This feels like one of the most critical life safety details in residential design, especially with kids around.
It is absolutely mandatory and completely non-negotiable in most places with private pools. The requirements are usually very specific. Typically, the pool must be surrounded by protective fencing that's a minimum height, often 1.2 meters. That specific height is chosen because it's generally considered difficult for small children to climb over.
And the gate.
The gate is just as critical. It has to be self-closing and self-latching, meaning it swings shut and clicks locked automatically. And the latch mechanism usually has to be high up, out of reach of young children. Often the gate must also open outwards, away from the pool area, making it harder for a child to push through.
Are there alternatives to fencing?
Sometimes. An approved, certified, load-bearing pool cover one that can safely support the weight of a child or adult if they fell onto it might be accepted instead of a fence in some jurisdictions. But the safety barrier requirement itself is universal.
Got it. And one last point on modern homes. Security systems. Things like video surveillance, VSS, or electronic access control, EACS, on doors. Does the code ever allow security measures to get in the way of getting out in a fire?
Never. This is the ultimate hierarchy in building codes. Life safety always takes precedence over security or property protection. Full stop.
So how does that work in practice?
While security features like cameras or keycard access are often required or desired, the systems must be integrated with the fire alarm system. This means that any security locks on designated exit doors must automatically release instantly upon activation of the fire alarm or during a power failure. There can be no scenario where security measures trap people inside during an emergency.
Life safety first.
That's
Always.
always.
So wrapping this all up, what's the core takeaway for you, the listener? We've gone through definitions, scope, structure, human factors. The big lesson seems to be that building codes aren't just checklists for, some official to tick off.
Not at all. They really are a highly structured, deeply interconnected system, and it's all built around achieving quantifiable performance goals, primarily safety, health, accessibility, and increasingly efficiency and sustainability. Every constraint we've talked about, whether it's the minimum width of that corridor, the fire rating of a wall, or the robustness design of the structure, every single one is a calculated requirement. It's tied directly back to protecting the health, safety, and well-being of the people who will use that building.
We've covered a lot of the what and why based on general principles, maybe global standards, but you always stress that context matters, right? Especially where the rubber meets the road locally.
Absolutely. And this raises maybe the final provocative thought for anyone involved in design or construction. Even with increasingly globalized standards and materials, local requirements and, crucially, local interpretations matter immensely.
Oh, so.
The ultimate challenge for any practitioner isn't just knowing the general rules, like the ones we've discussed. It's intelligently verifying and applying them in a specific place. Because the detailed requirements, the submission processes, even how different authorities or government departments interpret the same rule can vary significantly, sometimes even within the same city or region.
So you really have to understand that foundational system, that logic we talked about at the start.
Yes, you need that deep understanding of the foundational intent and the system's logic to navigate those local variations successfully and ensure your project is truly compliant and safe. You can't just assume. You have to check.
A really fantastic look behind the walls, peeling back the layers on something so fundamental. Thank you for decoding the philosophy of the built environment for us today.
A pleasure. It was great digging into it.